Hi, welcome back. Today we're going to take a look at contour plots. Now we've talked about contours before in this class, and you hopefully remember basically what a contour is a three-dimensional function on a two-dimension graph, on a 2D plane. And we see these all the time in our world. And a most common case is a topographic map. And in a topographic map, each curve represents a certain elevation. Right here, in the case right here, so like here, this curve on the outside represents every point along this function that has a elevation of 100. And you can go, so 200, 300, 400, and so on until you get to 600 right there. Now each one of these lines or functions are called contour lines or just plain contours. And what they do in a topographic map is, again, they outline the contour shape of the land. So let's look at this example and find out how we can apply this and our partial derivatives. So this topographic map shows certain elevations. Most of the time, the values of the contours change by the same value. And here, each contour is changing by 100. So we're going about every 100 feet, we draw a contour. We can use topographic maps to answer questions. For example, if we let the y-axis be north and south, and we let the x-axis be east and west, the function f represents the height or the elevation of our function right there. So the elevation is, so we are saying right here that the elevation is a function of our north, is our east, basically is a function of where our coordinates are going to be located. So let's see here. So let's apply calculus to this. The first one says, first question asks us to draw a line segment indicating where the slope is the steepest. Now when we're thinking steepest, we're thinking where the elevation itself is changing the fastest, the quickest. So we're looking for a very steep slope. So in this case right here, well, what do we think would happen? Well, hopefully we realize that the contours would be closest together. So where the contours are closest together, that is going to give us where we have the steepest rate of change. So I look at the graph, anywhere I look really steep, but this looks pretty steep here. See, right here I'm going from 100 to 200 feet, but they're not so close together, so not so steep. But if I go over here, the elevation from 100 to 200, it's a lot. Those contours are closer, which means that should be a little bit steeper. But let's see if we can find a place where it's even closer. Definitely not down here. Oh wow, look at right there. Look at right there between the 400 and the 500. Dang, that's pretty darn close together, so it's kind of hard to see, but right there, it looks like it's where it's going to be the steepest. And they want us to label that segment A. Now, if you're an avid hiker, you might be looking at this and saying, you know, I might not be able to walk that because that's very steep. I might need some climbing equipment for that. So you may say, I'll have to find another route. The next question says to draw a line segment indicating where the slope is least steep. Well, if the steepest is when they're closest together, this should be where the contours are furthest apart. Now, it's not so simple as just saying, oh, look, they're far apart, here's far apart. You really have to kind of think about it. They don't have to just be going east, west, north, south. They can go in some sort of weird direction. And if I try connecting lines, if I think of this as connecting lines, it might, connecting the contours might make it a little bit easier. So I might start taking a straight edge and just trying to measure some things. See the connection here between the 100 and the 200 contour? That's pretty steep right there. See that long I would draw a line right there. That'd be like a long contour. Like if this was a hill, you're basically walking along the edge of softly along the hill. You're not walking straight up. You're just walking along the edge to get to that height there, the next height. Or some of you guys might be thinking, well, what if I start from here? Is there any way that I can get it longer where the contours meet? What about something like this? It looks kind of like a little bit shorter. So for me, it looks like the longest contour might be somewhere down here. And I'll try to draw those out. So I might draw something like this where they meet. Now you do want to make it a straight line though, because remember, so I might draw this one. This looks like the longest contour. So we have a system here, a line here, a segment here that represents the least steep way to get up from the 100 to the 200, and they want us that to label B. Now, this is very important. Like if you're building a road up a mountain, you don't want to build a road on the steepest. You want to find the easiest way up. And when they build roads, they do something called what's called a zigzag pattern. And we see that all the time in roads. If you've ever driven in the mountains, you'll kind of see that. You'll see roads up a mountain that kind of go back, and we call them switchbacks. And basically what they're doing, they're building the road. Like if I want to go from here to the very top, I might say, okay, here's my road, go up to the one contour. To go to the next contour, I still want it to be the least steep. So that looks pretty least steep, but what if I go up here and I can keep going up that road? And these are called switchbacks. By doing switchbacks, we get the easiest way up a mountain. And it's not the shortest distance, it's not necessarily the longest distance, but would be the easiest because we go from one contour to the next. All right. So the next question says, at the 200 contour, label a point where a hiker would be increasing in elevation and heading due north. So they're increasing elevation and heading due north. Now, so let's think about what this means in terms of our derivatives. Well, if I think of f as my function, if I only want to head due north, there's no change in the x direction. So we don't want any change in the x direction. Well, how can I represent that no change in the x direction? We're talking about a derivative here. So we could write this as the partial of our function with respect to x has to be 0. So what this is really saying is, as x increases, f equals 0. In other words, there's going to be no change in the x direction here. The x does not affect our function. So we want to head straight due north. Well, if I want to head straight due north, well, where could that happen? I can, on the 200 contour, if I only want to head due north, and I want to go to the top. Remember, we want to go to the increasing elevation. So if I go here, but I only want to head due north. So if I put my point here and I head due north, I'm not increasing my elevation. I only want to be increasing my elevation. So that's going to put me somewhere down here at the bottom. At point C, I can only head due north and increase my elevation. Now you might be thinking, but what about if I go over here? I can head to the east and change my direction and head and elevate myself. But no, remember we said we can have no change in the x direction, so we can only head straight north. So it would be at the very bottom of our parabola. It's almost like we're looking for a minimum value. We're going to look at like that, find that minimum value on this right here. Because if I put it at any other point to head straight, to increase, if I head straight north, yeah, I'm increasing here, but I want to increase the most, I would have to head in this direction, and my x would change. We don't want that. So how would we write that? Well, we want to say as y increases, we want to say f increases. In other words, we only want f. We only want the north-south direction. So I can write that as a partial by saying the partial of f with respect to y is greater than 0. This is telling me as y increases, my function is going to increase. And we're only going to head in that y direction, or in this case, straight north, really. We only want to head north, so we don't have to worry about that part. All right, so let's take a look at another example here. Given the contour plot, this could represent all sorts of things. Now notice, we do have a function here. Function is in terms of x and y again. My function's in terms of x and y, where if my x value was 100, so like if I said x is 100, and I say that my y is 200, that's going to equal my value of my function, which is right here. So here's 100, there's 200, and that's going to put me on this contour. Well, what does that contour represent? 45. So my function value there is 45. So this contour says any point on this function has a height or a value of 45. This is what we mean by it's a 3D graph on a 2D plot. My x and my y-axis are my two dimensions, are my 2D. To get my third dimension, that's what the contour represents. The contour represents the height at that point. At, let's say 50 and at, what's that, 220 or whatever, my contour is on the 50 right there. All right. So we are here at point A. And what we want to do is we want to estimate the partial of the function with respect to x. So to do that, if I want to take the partial of my function with respect to x, what we are saying here is that y is constant. Okay. Now, that point A, this is our initial starting point, our initial value. And remember to get the final, and remember to get this, it was to get the change in something, it's always final minus the initial. So if y is a constant, what we're really looking for is how the function changes with respect to my x value, my horizontal value right here. So to do this, ready? I'm starting at point A. There's my initial value. We are going to increase. We always go increasing for now. Okay? So this line right here represents my change in my x values. So I can look at this as an average rate of change problem. Well, my x's are going to go from 100 to 200. So I'm going to write this as f of, now if I write this as a point right here, this is f of 200 minus my point over here, f of 100, 200, and I'm going to divide that by, of course, these are my change in my x's. My x's go from 200 minus 100. Now, let's think about what this is telling us right here. This is the value of my function. All right, these are my values. My values are those contours. So my contour at 200 is way up here at 40. The contour there is 40. So I'm going to go 40 minus, and my contour over here at 200 is 45. And I'm going to, of course, divide that by 100. And if we simplify this, we get negative 1 over 20. So what this is saying is, as x is increasing, my function's values are decreasing by 1 over 20. I'm going to apply these later on. If I want to find my partial of f with respect to y, now we're saying x is constant. So if I set this up the same way, but now only my y's are changing. So I'm going up right here. This is my partial with respect to x. There's my partial with respect to y. So to write this, we're going to go f of, so what's my point? My first one is going to be f of my x value is 100, whoops, comma, what's that about? 1, 2, 3, 4, so about 25, so about 50, so about 250, I don't know, minus f of 100, 200, over my change in my y values, 250 minus 200. And if we take a look here, remember we're looking at the contours now. The value is my contours. My contour at 100, 250 is at 50, minus my contour down here is at 45, and that's just going to be over 50. And we get 1 over 10. So notice, if this represents profit, which would we want to change? Would you want to change the x or you want to change the y? Well, the y, because that's increasing our profits. Well, if we change x, it's decreasing our profits. So another question we might ask, and we'll take a look at this in the next video, is the following. What if I ask the partial of f with respect to y? What is it saying? This is possible to ask mainly because as y increases, this is what we're saying, as y increasing, what happens to f? That's what this is really saying. As y is increasing, we're saying what happens to f? That's what this question right here asks. Alright, so take a look at the next video. We'll take a look at a few more examples. I'll see you then.